one circular came for uh, extra classes and exams and all should not be conducted on Saturday and Sunday. But EAE class is on before noon and afternoon is free slot. That's why we are conducting, going to conduct. I don't know, means so we have to talk to the dean. Then we will
Sir,
decide.
whatever is being taught till this week would come in the 23rd examination. 23rd examination.
No, starting
Only
from
up to
the
electromagnetism.
couple
Electromagnetic waves.
electromagnetic wave and couple oscillations are there.
And
Okay.
waves as well.
Yes, couple
Sir, but
oscillator,
electromagnetic
waves,
waves
and
are,
electromagnetic wave.
sir, but electromagnetic waves
Sir,
have not been
sir,
completed yet.
damn part and all is not there, no, sir.
The Fourier series will come or not?
Yes, yes.
Sir, damped oscillation is not there, right?
No, no, no.
Oh.
Though those sections means the what was covered in class test 1 will not come in the class test 2.
Sir,
Yes.
The Fourier series is going to
sir,
come.
after,
Yes, Fourier series will come.
sir, after the confirmation of the timing of the examination on 23rd, please send us a mail, sir.
So I guess section 1 and section 2 students are not having any problem on 23rd afternoon.
No, sir, no problem.
Okay.
Hello,
Hello.
sir.
Yeah.
Sir, on 23rd, we have an NSO class.
NSO class in afternoon?
Yes, sir.
No.
Yes, sir. We have class from 6:30 around.
6:30 what? In evening.
Yeah.
So then this will be over by 5.
Okay. So, sir, what is
Pardon me?
on 23rd?
Sir, 23.
Sir, what is timing of test?
Most probably at 3 or maybe 4, depending on the availability from the Moodles.
So the
Sir,
Fourier
maximum
transform
equations
will
are
also come.
time duration, sir.
Same 1 hour, 10 minute or 20 minute.
Okay, sir.
The
Sir,
Fourier
maximum
transform
equations
will
is
also
there in
come.
that
The
case.
pattern will be
Sir,
same.
can you tell till which lecture will the portion be for the next
Yes,
test?
sir.
Just after forced oscillation, means starting from the couple oscillations, and then we have waves, Fourier series, and then we have EM wave.
Sir, but EM wave have not been completed yet, and I have not done any tutorial for EM wave.
Who told you it is not completed? Have you attended
Sir,
all the lectures?
sir, but our TA has not completed any tutorial for EM wave.
This week you will get the tutorial for EM wave. Means, your tutorial is on Wednesday and Thursday and Friday.
Wednesday.
Yeah, so it will be completed. Okay, so shall we start? Okay, so we started this course with the mechanical wave, starting with the oscillations, and then we have many mass spring system, and then we learn about the mechanical wave, and then we move to the second part of the course where we learn about the um, electromagnetic wave basically, and then we learn about their propagation in different medium using some boundary condition. So continuation of that, we are just moving to the
Sir,
optical wave. Yes.
sir, there was a doubt on Laplacian. divergence and curl property in previous class.
So
That cross and dot thing.
maybe you can ask later. First, let me finish
Okay.
this. Okay. Okay. So basically, you have learned this superposition of waves in 10+2 with some simple method like algebraic method. You have learned this. Here we are going to learn slightly more advanced how you can superpose many waves, but just think about this. Why we require this superposition of wave? Any guess?
In signal processing.
So to study the
In signal processing, sir.
Signal
To
process.
increase the
Yeah, it
to
has
increase
many
the
application in sciences. So just take a very simple example. Okay, you have a bulb and it is giving you various kinds of waves, wavelengths or different frequency. So if you want to just superpose those waves, okay, then it will be very difficult if you have different frequency or different polarization or different amplitude and phases. So simple algebraic sum will be very difficult to do. Okay, so and the application of why we require this superposition, just like in case of laser, you can see many different atoms are in excited state, and when it goes to the de-excitation of these atoms, then it generates some photons, and corresponding to these photons, they superpose each other, and then it comes out of the one of the output from the mirror, and then you get the lasers out of this box, just like we have seen in the pointer. Okay, so how you can increase the intensity if you have many more waves superposing to each other, then you can increase the intensity and so on. Okay, and if they are in out of phase, then you will not see those kind of intensity. Maybe it will just cancel out and you will not have any output. Okay, so just we will slowly see how the superposition of wave happens, and what is the use of the superposition principle. Okay, so just starting with a simple example. So superposing several sinusoidal waves with same frequency and polarization, maybe you have different amplitude and phases, then you can use either algebraic method or complex method or phasor addition to get the output, and that will also give you, if you have same frequency, then same frequency you will get it here, polarization will be same, and different amplitude and phases will be there. So just see this expression E of xt. So you have, I'm just writing E, maybe you can have some Y or so, but it is a function of a space and time. It is varying in space and time, and this E naught is the amplitude. And what we have learned in the EM wave, you have the time part and you have the space part. So omega t minus kx, and I'm including this epsilon here in the space part. Okay, so we are just writing this resultant as E naught sine omega t plus phi, and this phi is for the phase, the space part of the phase.
Sir, please
okay,
start the recording.
it is already done, huh? Yeah, recording has just started. Yeah. Yeah, recording is started. So do you see this?
Yes, sir.
Okay, so this alpha is the phase basically we call, and this include the information about the space part. So this is we are writing here minus k of x plus epsilon. Okay, so let's take very simple example that you already know. Okay, so just take two simple wave having similar frequency but different amplitude E01 and E02 and different phase. So alpha 1 and alpha 2. The resultant will be, you just sum this E1 plus E2, and how you sum, you just expand this term like this and expand this term, and then you can write in terms of sine omega t and cos omega t, and you take this whole bracket thing as E naught cos alpha, and for this bracket you take E naught sine alpha, and the final wave, when you write this, then E naught is the resultant amplitude, and you can express this E naught as just by taking the square of this term and the square of this term, sum these two, then E naught square as amplitude square of first wave, then amplitude square of second one, and then you have cross terms. Okay, this alpha you can write as the ratio of these two. If you take this sine to cos, then that will give you the tan alpha. So this is for simple two waves having similar frequency and different amplitude and phases. Okay, now if you just think about this term, okay, so alpha 2 minus alpha 1, if it is a constant over time, and then E1 and E2 are coherent to each other. So we will learn what do you mean by coherent or incoherent just in few slides later. Okay, so if it is in phase, that this what we writing here, this alpha 2 minus alpha 1, okay, this one. So if it is in phase, this delta is 0, then you can see if you sum these two, then the black solid curve is the resultant of this dotted and the faint gray waves. You can see you have a maximum corresponding to this, and minima when it is approaching to this one, then you have this one minima, maxima, and then minima, and so on. Okay, so very simple. And when this delta is you can say pi is out of phase, then you can see the resultant is less than this whatever you have the input waves. Okay, one assumption we can take here, if the amplitude of the first wave is very high compared to the second one, then this tan alpha, where you write this expression, then alpha becomes alpha 1 corresponding to the highest amplitude wave. And similarly, if E02 is greater than E01, then alpha becomes alpha 2, and so on. So the meaning is which one will dominate if you have very large amplitude of the wave. Okay, so this is for the simple two waves we have added, and we use the method algebraic sum to get the superposed wave. Okay, now these cross terms is called interference term, and condition for maxima or condition for minima you can set by taking this delta as 0 or plus minus 2 pi and 4 pi and so on, and for minima it is plus minus pi and so on. So just write in terms of the space part. Okay, so for alpha 1 we can write kx1 plus epsilon 1. For alpha 2 you have kx2 plus epsilon 2. So you can write this as k is 2 pi over lambda, and then you have x1 minus x2 and epsilon 1 minus epsilon 2. Okay, so if epsilon 1 and epsilon 2 is the same, then you can write this, express this as n equal to c by b is a refractive index, speed of light, and the velocity of that wave in particular medium. So you can express this as lambda 0 upon lambda. Basically, you know this expression the optical path difference as 2 pi over lambda naught n times x1 minus x2. Okay, so what you have is, for the coherent wave, this epsilon 1 minus epsilon 2 is constant. Okay, and this one n times x1 minus x2 is called optical path difference. Now suppose you superpose many waves and you can use the algebraic sum as E equal to summation of E0 I varies from 1 to n, and you have cos omega t plus minus alpha I. Okay, and now the resultant is E equal to E naught cos omega t plus minus phi, and you can express what is E naught and what is this alpha. So E naught square is, you can get it by summing over E naught I whole square, and I vary from 1 to n. And for the cross terms, you have E0 I and E0 j, and you have cos alpha I minus alpha j. Here it is very important to note this I vary from 1 to n, and j is greater than I. Okay, and you have this 2, it says, because you have repeating terms, so this 2 is for that. And the tan alpha, similarly, you can take the ratio of those two amplitudes with the phases. So summation of E0 I sin alpha I, and I vary from 1 to n, to this ratio E0 I cos alpha I, and this is 1 to n. Okay. Yes.
Sir, here we take
Sir,
vector quantity or scalar
Which
in
one?
finding tan alpha. In
Yeah,
finding
so
tan alpha, E naught sin alpha 1.
yeah. So these ones, this basically you are doing some kind of a vector sum. We will learn slightly in next few slides what we mean about this tan alpha and E naught. Simply, if you are just representing this with sin omega t plus alpha 1, so this also gives you some kind of this is sinusoidal function. This alpha is giving you the resultant phase. When you superpose, then what will be the resultant phase of the output wave?
Okay, sir.
And this information, what alpha is, when we are writing this, is giving you, okay, so just we have done for the two waves, okay, this E1 and E2, and then you can see here this is the summation over these two sin alpha 1 and sin alpha 2 with their amplitude, and cos alpha 1 and cos alpha 2 with their amplitude. Okay, that you assume here, and you take this ratio of sin to cos, then that is giving you alpha. Okay, so this is the resultant phase of the superposed wave. Okay, so if you have n number of waves, then we are just writing this summation of this E0 I sin alpha I, and in the denominator we are writing summation of E0 I cos alpha I. Okay, like this. Okay, so now we can take very simple, just like I gave you example of if you have a just simple ordinary bulb, then the phases is random. Okay, so for random rapid nature of the phase change, then you can have this time average of alpha I to minus alpha j, that will give you 0. So the amplitude square, this one. Okay, so these cross terms are 0 for a random phase if you take the time average, so that will give you only the E naught square contribute from the individual amplitude, and if you take this as 0, then you have this part, and if you write for n number of waves having similar amplitude, then you can write n times E0, either of any wave you can take, E0 1 square. Okay, so the resultant flux density, or this is basically giving you intensity. Okay, so intensity will be n times intensity of any one of the wave. Only this happen when you have a random phase. Okay, now suppose if this alpha 1 and alpha 2 are same, it is called coherent source. Okay, in that case, this term, okay, this term will contribute, and this will be whole square. So each amplitude you can write for any one wave. So we are just taking E01. So this term will give you n square times E01 whole square. So intensity here will be n square times the intensity for the first or any one of the source. Okay, so you can just see the random phase, or you have a coherent phase. Okay, the difference between these two. Okay, yes. Yeah.
I can understand what is random phase.
Random phase means okay, so there is no correlation. We will come back for the coherence when we deal about the spatial and temporal part. Okay, but just for time being, you take it this as random means these phases are it can take any orientation. It doesn't have any fixed phase. When it originates from the source, then their phases are rapidly changing. Okay.
Yes, sir.
Okay, that is the meaning
Sir,
of.
can you show the previous slide, sir?
Yeah.
Do you write n square E01 square, sir?
Yeah, this one, huh?
Yes,
yeah,
sir.
so this is whole square term, no?
Please explain that why is there n square term?
Oh, n square term. So this is whole square term is there. This is whole square term. So you have n times E not 1, and then whole square term. So n square is there.
Summation would be outside of the square, sir.
No. Summation is inside. That's why it is giving you n square term. If it is outside, then you will come back to the previous one.
Sir, whole square is completed. See above.
Yeah. Here it
Sir,
is.
please show the previous slide. Previous slide. Okay, sir.
Sir, how the flux density depends on only the amplitude of one wave?
Oh, any one you can take. Just for simplicity, we are writing one. Okay, so in this case, if you have n number of waves with similar amplitude, but if the phases are random, then the intensity will be n times then any one of the wave. But if the phases are constant, or you can say it's a coherent, then intensity will be n square times any of wave.
Hello, sir.
Yes.
Sir, but the density of any one of the source will be vary from one to each other.
Yeah, that is the meaning. So if it is varying from each other, then that is a random.
So, sir, how can we take any single energy source, sir?
No. See, if what we are considering here, if you have n number of waves having same amplitude, but the phases are random, then the time average of those phase difference, this part, the interference part, is 0. In that case, if you just want to know the intensity of the output wave, that will be just the n times intensity of any individual wave. And if they are coherent,
Sir, give some examples, sir.
Okay, so just like in case of laser, the output photons are having same frequency and amplitude because they are dropping from the higher state to the ground state, and the energy of these states are fixed. Okay, so having same amplitude, so if many photons are superposing and having constant phase, then intensity will increase. So you can see for the pointer laser, this is in the order of microwatt to milliwatt. If you go for the bigger laser, then that have some 10 milliwatt or 15 milliwatt or 50 milliwatt. If you go for higher number of photons, means you generate infinite, not infinite, means very high number of photons, then you can increase the number of increase the intensity of that output laser. So you have more wattage. You can have maybe 500 milliwatt or 1 watt or so on. So this depends on how you are superposing the wave. And if it is random,
Previous slide.
this the previous slide.
Yes, sir. No, sir. No, sir. This one. Yes, sir. Yes, sir. Sir, suppose we have two wave equation.
Yeah.
So then its resultant amplitude will constant, na, sir? According to your formula, it will vary, sir. If we Sir, suppose we take two equation, two wave equation, and then
consider this as I vary from 1 to 2 only.
Then its flux density will constant, na, sir? But in other formula it will not constant, na? You say anyone you will put it E01 or E02.
You can put any one. So it is constant. It is just taking n times individual one. If it is random.
Sir, I can't understand.
Sir, E01 is equal to E02. Okay, sir.
Why, sir, E01 equal to E02? It is not given, na?
No, it is not given. But what I am telling you here, you have equal amplitude, but phases are random. Okay, so at this cross terms, this term, the time average will give you 0. Only this part will be remaining. Okay, maybe I will put here with the similar amplitude.
Sir?
Sir, I can't understand, sir, what you want to say.
What didn't you get it, Ritik?
Sir, flux density, sir, this one.
Flux, how what do you mean by flux density? Basically, you want to measure the intensity, yes, at a particular space and time.
Yes, sir.
Okay, so suppose you have n number of waves having similar amplitude and frequency, but phases are random.
Oh, yes, sir. Yes, sir. Now I understand. Means similar.
Yes.
Their amplitude is similar, no?
Yes, amplitudes are similar, but phases are random. So there is no correlation of one wave to other wave.
Yes, sir. Yes, sir. Now I understand.
And in the other case, the waves are correlated. So when the waves are correlated, here also you have similar amplitude and frequency, but the phases are coherent. Okay. So in that case, this is n square times the individual one. So intensity will, yes.
Sir, I did not get this, sir. How you have written E naught square is equal to sigma I is equal to 0 say 1 E0I whole square.
Okay, very nice. Okay, so what you do, just take 2. Just take I as 1 to 2. Okay, so what we will get? E01 square plus E02 square plus 2 times E01 and E02. Because I should be 1 to 2 and J should be greater than I. So only one condition you have. Okay. Got it? If you are putting I equal to 1, then you will get 0,
1.
E0,
Yes,
1.
sir. Yes, sir. Yes, sir.
Okay. You got it? So you will get E0I E01 plus E02 whole square. Got it? So you can write for.
Sir, I was asking, sir, that previous slide.
Yes.
Sir, here alpha and alpha I and alpha j are independent of time. So why we are taking time average?
Okay, so independent of time, yeah, it is random, so it is not depending on any time. So if you take this, the time average.
Yes, sir.
Means suppose you have a source, a random source, and yes.
So if it is independent of time, then why is 0? Then anything can be there, because if alpha is independent of time and we are taking time average, if cos of alpha I and alpha j are like 1, then a time average will be 1 only. Then why 0?
No, we are not getting. So this alpha I, this difference we are just talking about. Okay.
Yes.
Difference is the alpha I minus alpha j. So this is from the two different source. They are not correlating. You cannot put alpha I and alpha j are same.
No, sir, I am not taking it same, but it is independent of time. So
yes,
it will
independent of time, but not same.
Yes, sir. Suppose if alpha I is minus alpha j is like pi by 4, it is constant with time.
No, that should be also, it should vary with the time. That is the meaning. If it is a constant, just go back to this one. If it is constant, see here, if the difference alpha 2 minus alpha 1 is constant over time, then these are coherent to each other.
Yes, sir.
That is varying. It is not constant. That's why variable is there.
No, it is constant with time, no, sir.
No, if it is constant with time, then this will maintain the phases, is a phase constant, will be not changing with time. Then it is these two waves are maintaining some coherence.
Yes, sir. Then how, sir? Average is 0, sir.
Here there is no phase constant. That difference is varying with the time. That's why if you take the time average, then it will give you 0. If it is a constant, then time average will give some value.
Yes, sir.
Yeah, so that is not the case.
Sir, but if alpha I is individually independent of time and alpha j is individually independent of time, then how the difference will be like dependent on time?
Why not? Why it will not depend on time?
Because sir, individually they are not independent. Like it is a function, like a constant function minus a constant function. How it can be like a function of time?
No. See, that is the meaning of why we are writing this t here. If you are saying
it is a function of time.
Yeah, so this is function of time. This is randomly varying with the time. You cannot predict
okay, so
their
alpha I is like is vary with time.
Yes.
But the given like alpha was only function of x and phi.
No. Just see what we wrote here. Alpha is kx. This one. See.
Yes, sir.
This phi kx, and you have epsilon.
Yes, sir.
Yeah. So this alpha is changing with time. So this is the phase part, and this is not constant.
Okay.
Epsilon
is
independent.
The source is like
difference of alpha is constant only then it is coherent.
Yeah, only then it is coherent. Maybe 0, maybe some value, doesn't matter. If it is the difference is constant, then you can have a coherent wave.
Okay. Yeah, I got it.
Okay. So now we have applied very simple algebraic sum method to superpose many waves, and you can see the difference between the random phase and the coherent phase, and you can just see the amplitude or intensity, how it vary with n number of waves. Okay, so for the random phase change, it will be just n times the intensity of the individual one. Yes.
Here is n square or only n?
In the random phase, it is n only.
Sir, in previous slide, it is written the n square.
No. In the next slide, it is n square. So for the coherent source, it is n square.
Oh, yeah.
Okay, so now you can use a different method. It's a complex algebra, and I think we have done this kind of superposition in the mechanical wave, and we are just refreshing those things here. So for one wave, you can write this E0I e raised to I alpha 1 plus omega t. This alpha 1 having the information about the space and the phase factor, okay, and the resultant n wave for n number of waves. Okay, you can write this E I omega t having similar frequency, then this part will be just outside of this bracket, and then you are summing over the amplitude and their phases. Okay, the complex amplitude of the resultant wave, the bracket part, you can write E naught e raised to I alpha as summation of E0j e raised to I alpha j, and j summing from 1 to n. Okay, and if you want to, if you want to know the intensity, so you have to just take the square of this amplitude, and then you have E0 e I alpha and their complex conjugate, and see here. So if you just do that, then this will minus sign will come here and this will cancel out, so you will get just the E naught square. Okay, you can just take very simple example. If n is equal to 2, then you will get back to the similar expression what you have learned in the superposition of wave with the algebraic method. Okay, another one you have is phasor method. So we have given you the definition of the phasor, that this rotating arrow and associated phase angle, that is the phasor, and you can have this organ diagram where you have imaginary axis and the real axis. Suppose you have a vector here A, then you can write their projection as A cos omega t if it is omega t here, and then you have A sin omega t. Just a vector, resolving this vector on the imaginary and real axis. Just taking very simple example here, adding two phasors. So it is given y1 as 10 sin omega t and y2 as 8 sin omega t plus 30 degree. Okay, and resultant is ER sin omega t plus alpha, and you have to find out this ER, the resultant amplitude, and this alpha, okay, resultant phase. So very simple. Suppose you are just taking this as this as amplitude. This is for the first one, and this is for the second one, and here you have the ER, it's the alpha. The resultant will be if you just take the projection of this one, then it will give you 8 sin 30 and 8 cos 30 here, and you can see if you add this, then resultant wave having the amplitude 17.39. So very simple. You have learned this in 10 plus 2. This is a vector sum you have, basically vector sum you are doing, but this is very simple for 2-1. But suppose you have 3 or 4 or many different phasors. Okay, so here we are just taking very simple example of having similar amplitude and frequency, but the phases are different. Okay, so the different if you use the phasor addition, then you can write this as ER sin omega t plus alpha, and you have to find out this ER and alpha, and you can do like this. Okay, just by doing this phasor addition by taking the projection over any one of the page. Okay, so this is, we are just taking on the first one, so that's why you have cos 0 here, then you have cos 60, and then you have cos 30, and then on and similar to all. Okay, okay, so now phasor addition, basically what we learn is suppose you have any vector in this one, and you rotate it by alpha 1 or alpha 2, just like this one, then you can take the, you can basically you can write the resultant like this. This is
Sir?
written for only 2. Yes.
Sir, here alpha are constant, no? Alphas are.
Yes, here basically we have taken alpha 1 and alpha 2 as a constant, but we will see in the next few slides that if you vary this alpha, okay, means
Yes, sir.
either random or you have a fixed coherent and so on. So similar things we are learning in different methods. So algebraic sum, why we go for this phasor addition or for this complex algebra? So this makes life simple. Okay.
Okay, sir.
Okay, just another example we have, the amplitude is like 1, 3, 4 and 2, and then you have some angle given here, okay, just like for this one is 0, 45, 120 and 90, and when you just take the algebraic sum, the vector sum, then you can see the resultant amplitude as close to 7.5 and pi is 81 degree and so on. Okay. Okay, so basically you will see the superposition of large number of phasors of equal amplitude and equal successive phase difference here. So let's try to find out using the phasor or complex algebra. Okay, so here you have E naught e raised to I omega t minus kx, and for E2 you have some phase minus phi, you have minus 2 phi, and similarly you have minus n minus 1 phi for n. Okay, so for 1 you have 0 here, for 2 you have 1, for 3 you have 2, and so on. Okay, now if you want to sum this, then you can use very simple method like just E naught, you just write it all the summation. Basically you just plug in all those values here, take the common thing here, and you will get a series. Okay, and if you sum this series you will get it E naught. Okay, just work out. Okay, E naught e raised to I omega t minus kx is common, and then you have this whole series. So GP series you have, and then sum of this GP series you can write as 1 minus r times raised to n, and then you have 1 minus r. Okay, can you just find out this term from this one? Just take common in the numerator and denominator. Can you work it out? Just two
Yes, sir,
steps.
it is coming, sir.
Yeah, good, very nice. Okay, so now this is the summation for n waves having similar amplitude and successive phase difference. Okay, and you just consider n equal to 2, then the resultant amplitude is like 2 E naught cos pi by 2, that you can confirm either from the algebraic sum or so on. Then the intensity, again you take the square of this one, then 4 E naught square cos square pi by 2, and if phi is 0 you will get maximum, and so on. So you can work out these things. So basically you can write I equal to I naught cos square delta by 2. Delta, here you have the phase difference, and you can see this expression many times in optics. We will come across this expression in double slit or biprism, Michelson interferometer. So these things, this terminology we will explain later. Just you can take it for granted here that this intensity varies like this. And double slit, you know, Young double slit experiment in 10+2. We will all, I think you know biprism, but you might not know this Michelson interferometer, but we will go through all these terms later. Okay. Okay, so now you can do this similar kind of superposition using n phasors. So here you have similar amplitude and successive variation of this theta. So you start with this A with 0, superposing on this one, you have theta, then 2 theta and 3 theta and so on. The amplitude is still A. So you can write this A as 2r. Okay, so what you can do, you just take a circle of radius r, okay, and you can this variation is theta and 2 theta and so on, you have n theta. And so basically you can write this as this resultant. This is the resultant you have. So this is 2r sine n theta by 2 and this phi is n minus pi by 2. You can do it like this also. Okay, so any doubt with this? This is just a way, basically you will get it from the similar either complex method or
the radius of this circle, sir.
Okay, that is a very good question. So you have to find out this r. You know A. Okay. Okay, it will be more clear if you take this continuous or something like that. Hello.
Yes, sir. Yes, sir.
Yeah. Okay. So suppose you are taking a very large number of source having similar, very similar to this case. Yes.
So there should be capital A, sir. Below, sir. We are finding capital A, no, sir.
Yeah. So basically, you are doing this vector sum, nothing else.
Yes, sir. Yes.
Okay. So suppose n is very large, you can take it to infinity, and a tends to 0. But and theta also tends to 0. So in that case, this n times theta, we are just taking this as a constant and 2 alpha. Okay. And n times a is the amplitude a naught, which we can write as square root of I maximum 1. So
Excuse me, sir.
Yes.
So why here A is tends to 0, sir? Actually, the amplitude
So
is constant, na, sir,
suppose
of
you,
every vector.
No. This we are taking, this is a continuous infinite number of beams. Okay. So in that case, you have n number. You can consider this as a point source. Okay. Suppose you have just a point source arranged on the periphery of the circle. Okay.
So after some time, sir, it will complete the circle, na, sir?
Yeah. You are right.
How the n can be infinity, sir?
No. What we are taking. Okay. So this n infinity means you have so many sources.
So A is constant or sir something else?
For this case, A is constant.
And for the next slide?
For the next slide, what we are taking this A as tends to 0. But there.
So there should be minus n.
Minus n.
Sir, e to the power minus I n theta and e to the power minus I n theta.
This one?
Yes, sir. Minus is missing, I think.
Oh, let me check it. Okay, so no, it's fine.
Here also should be minus.
So what is the formula? 1 minus r raised to n, a times r raised to n, and divided by 1 minus r.
Yes, sir. And here r is e to the power minus I. So minus is missing, I think.
Yes, sir. There minus sign should be present, sir.
Then the formula you written is coming true.
Okay. So I will just correct it. Okay.
Okay.
Okay. So yes, everywhere I think it is propagating because it is copied from here itself. Okay, sorry. So I will correct this one and the sign is there. Okay. Yeah. So for the continuous infinite number of beams, n is infinity and a is 0, but their product n times a, that is the meaning of continuous source. Okay, you have finite amplitude. Just like you consider a filament in bulb, and each point, so the aggregate, you will get some amplitude. But if you look at the continuous source for individual point, okay, then how you can write this?
Sir,
A tends to 0 and n tends to infinity, that is giving you some finite amplitude. Yes.
sir, if beam will complete the circle, the resultant will be 0.
One by one. So many background noise are there.
Sir,
Hello?
sir,
Yes.
I was asking that if beam will complete a circle,
Beam will complete the circles, then what? It's fine. What is a big deal?
then resultant will be 0, na sir?
Yeah, the vectorial is, yes, definitely the vector sum of all those vectors, if it is coming back to the same position, then it will be 0. Yes.
In this case, the beam will not completing any circle.
In this case, no. Yes, you have suppose array of lines or any.
Sir, but n is tending to infinity, so it will definitely complete the circle, sir. So as a is tends to 0 and so n is tending to infinity, so it will definitely complete the circle.
No, suppose it is.
Yes, sir. It should come back to the initial point.
In that case, this R will be also very large. Just think about this term. Okay.
Sir, but the resultant will be 0, whatever be R, but the resultant will be 0.
If it is completing whole circle, definitely.
Sir, but we have written that n tends to infinity.
Yeah,
Not so many constants.
Yeah, n tends to infinity. Then don't come to this slide for this case.
So it is just for continuity.
Yes, just for continuous. We are just talking about you have a continuous infinite number of beams. In that case, you have some resultant amplitude, but n is very large. Corresponding a should be 0, so their product should have some finite value.
Yes, that is for continuous. You have assumed n tending to infinity and a tending to 0.
Yes, yes, yes.
Okay, sir.
A circle is not completed.
Yes, yes. This is not related to this circle. Okay.
Okay.
Sir, how n theta tends to 2 alpha?
Yeah, so if you just talk about this n times theta, so in this case, if n is infinity, very large number of source, then and a tends to 0, then this difference between this consecutive theta will be 0. But again, with the similar thing, n times a, it's like we are talking about the resultant amplitude that is having a finite value. Similarly, the output wave have some phase, and we are writing that phase as 2 alpha. So n times theta is not 0. It will give you some phase. N times a will give you some amplitude.
We are assuming it as a naught and 2 alpha.
Yeah, it is a naught and this is 2 alpha.
Okay, sir.
Just for simplicity, we are assuming 2 alpha because here you will see.
Yes, sir. Something will cancel in calculation.
Yes, yeah. So if you assume this, then the resultant what we are writing for n number of sources having a continuous variation in a and theta, then you can just take those summation, the final expression, and here is minus sign, here is also a minus sign. In that case, again you will get the same expression, just take out n theta by 2 common, okay, and from here theta by 2 common, then you will get this term and the resultant You can write in this fashion. Okay. So you can use this property to find out, just replace n theta as 2 alpha. Here sin theta by theta form, when theta tends to 0, then you can write 1. Use the similar property. Can you just work out and get it this form? Just do it, just one step is there.
Yes, sir, it's coming.
Yeah. Okay. So now you can write this whole term as this amplitude A naught. This we are writing this n times A as A naught. Then you have this term sin alpha upon alpha, and then you have this phase factor. So we are just writing alpha prime. What I sent you day before yesterday, is a prime is missing there. Okay. And if you want to calculate the intensity, just take the complex amplitude and multiply with this amplitude. That will give you this term A naught square sin square alpha upon alpha square. Okay, so now time is.
Sir, previous slide, 1 second.
Yeah.
Sir, how that n come here? N is sin alpha by alpha.
Oh, okay. So can you just work out this term? Who got this?
Sir, theta will be cancelled then.
Theta will be cancelled? How?
Yes.
Sin n alpha should be there, sir.
Huh? Sin n alpha? No.
By
this
alpha.
is n theta. N theta you can replace with 2 alpha.
Then how n is it, sir? One extra n is.
So we are taking limit when theta tending to 0, sir.
Yeah, theta tends to 0.
Then limit will be
Then,
1. Here and
oh, you are ignoring n.
Sir, n but
You
n
have to take n as infinity and theta as 0. For this term, you have to divide by theta by 2, and then theta you can write in terms of alpha. You got it? Just work out. It's very simple. Okay, so just do it. Sin n theta upon 2, that you can write sin alpha. The numerator is fine. This one. When you write
yes, sir,
n
understood
theta
now.
is 2 alpha.
Yes.
Now about this term.
Sir,
Okay.
approximation has been taken. Yes, understood.
So now theta you can express in terms of 2 alpha upon n.
Yes, sir.
So alpha upon n, and then you divide and multiply by this term. Then when theta tends to 0, whatever you write alpha tends to 0, then it is 1, and that will give you n by alpha. Okay, this term.
Okay, sir. Understood.
Sir, can you once more explain how that 1 minus e to the power by 1 minus e to the power is transformed into sine by sine?
Oh, this one.
Yes, sir.
Okay. So you just take common. This is extra term you are getting here. You just take common minus I n by 2 theta from the numerator, and from denominator you just take minus I theta by 2. If it is, so basically what you had here, minus sign is missing, so you just take plus 1. Okay. So n theta by 2 times I, you just take it common for this term. You just take common from numerator and denominator.
Okay, sir.
Then got it? Then you just use the Euler formula that will give you sin n theta by 2 and sin n theta by 2. Okay.
Okay.
I will cancel out. It's fine?
Yes, sir.
Okay, good. So should I continue or is fine? Maybe from the next class we will talk about coherence.
Time is over.
Yes, sir. In next
Yes,
class.
sir.
Yes, sir. Time is over, sir.
Okay.
Yes,
Thank you, sir.
Can we leave now?